All right. Hello, everyone. Thank you for joining us for another Telops webinar. We will begin today's webinar about now. My name is Chris Giesige. I am a field applications engineer with Telops, and I will be acting as your host today. And I'm very excited to also have with us our guest speaker, Jesus Belmar, who will be presenting about his research and some of the cool stuff that he's involved in. First, I just want to get a few housekeeping things out of the way. I want to let everybody know that this webinar is being recorded and that we'll be sending it out afterwards. After the webinar is complete, we'll be sending out a follow-up email where there'll be a recording and a link to download or view this webinar. We also encourage from our audience questions. Please, if you hear anything that is of interest of you today, or if there's anything that you want to know more about, feel free, use the GoToWebinar questions tab and ask the questions. We'll save some time towards the end of the presentation to try and answer a few questions live. And any questions that we're unable to get to live, we will provide written responses in the follow-up email that we'll be sending out to everybody. Okay, I think we can get started here. Our presentation here today is focused on some really cool aspects of hyperspectral imaging, in which I will kind of give a brief introduction of hyperspectral imaging. That way, for anybody who's not too familiar with it, we can at least get some sort of a general background about what it is. So an outline for today's webinar is I will give an introduction, introduce you to Telops, kind of give an overview of our applications for our infrared imaging, and then again, a little bit of a background for hyperspectral imaging as well. After that, I will turn the presentation over to Jesus, in which he will discuss the cool research he's involved with, measurement of unburned methane emissions in laboratory flames using mid-infrared hyperspectral imaging. And then once Jesus is done, we will have some time for a little bit of Q&A. So to start, Telops was started in 2000 in Quebec City, Canada, and it now employs over 100 people. It has established itself as a world leader in thermal infrared imaging solutions. We now offer innovative solutions for aerial methane leak detection and quantification. Several years ago, we joined the Exosense group, and we also have a new acquisition of LRTech. These are some of the products, some of our cameras that we have. This is the product line, the hyperspectral cameras, which we'll be talking about today. We have multispectral cameras. We have a new high dynamic range camera that allows for a 900 degrees Celsius range in a single exposure time. We're very excited about that. We, of course, have our high performance fast cameras that come equipped with high frame rates or really high spatial resolution. And then we also have another addition to the team, which is our entry level, a little bit more of a compact camera. Those are the Radia cameras. Some of the main applications used for our cameras are ballistics, combustion engines, IR signature, gas detection, which we'll be talking about today, cold spray, experimental mechanics, additive manufacturing, mineral identification, and fire research. So a little bit of an overview about hyperspectral imaging. We can see, if you guys can see the laser pointer over here, these are the images on our left are our hyperspectral cameras. We have the HyperCam here on the top left, our HyperCam Airborne Mini on the top right, and then on the lower is our HyperCam Mini XLW. So with hyperspectral imaging, I have a measurement that consists of a series of images, which get recorded at different wavelengths. So essentially, in each pixel, every pixel contains a spectrum of those images and a spectrum of the wavelengths. Now, it's great for real-time chemical imaging and quantification, and allows for volatile organic compound detection, identification, and quantification of gases. If we look at this image over here on the left, this is a pretty good depiction and illustration of how our hyperspectral cameras work with our FTIR technology. So the hyperspectral camera is capable of decomposing the infrared light into its basic bands of contiguous wavelengths. It has a moving mirror that translates scanning wavelengths into incoming IR radiation, which are modulated in time. And then a fast Fourier transform converts these data from a time domain into a frequency domain, where an IR spectrum at each pixel is created. And this creates a hypercube, essentially. So you have a multidimensional cube inside of each one of these pixels that contains a spectrum. Okay, the spectra, the fundamental information about the IR absorption and emission characteristics of the target that you are trying to capture. Okay, some great benefits of this is this allows for high specificity of detection and identification, and the ability to detect and quantify gases such as methane, sulfur dioxide, VOCs, and many more. Okay, there's a few case studies that we have from Telops with our hyperspectral imaging. This is a hypercam that was used on a tripod at the highest spectral resolution possible with averaging of multiple data cubes, which increase the signal to noise ratio. This involved mapping and quantification of a methane gradient above a very nutrient poor lake. And we can see here that this red color is methane that is kind of bubbling up from this lake, and it occupies this whole image here. So if we look over at our color bar, we are looking at the methane mixing ratio in parts per million. So I was able to detect this and quantify the methane in parts per million that's kind of eking up out of this lake here. Another case study that we have is with our airborne hyperspectral imaging. And if we look over at the images on the left, essentially what we're doing is the imager, the sensor is flying over this TADI test platform in France and looking at methane gas release. And if we look at these images, we can see these colors in the images. As it's flying over these structures, it's able to detect the methane that is being released by them. Okay, we have powerful algorithms that allow for real-time quantification of gas plumes in path length units of parts per million and gas total mass in grams. In our post-processing, we factor in gas velocity values, and that leads to gas flow estimates. So we can see underneath the images that we're able to retrieve flow rates from this in grams per second. Those, of course, are only a couple of case studies that we have with our hyperspectral cameras. But of course, it's got a proven track record throughout the years. The system's been used in numerous contexts and deployed to different parts of the world to detect and identify different chemicals. It's able to detect other things such as ethane, sulfur dioxide, MTB, and so on. So now that's kind of a little background into hyperspectral imaging there. Hopefully, if anyone who wasn't too familiar, at least kind of understands a little bit about it and is able to see the uses for it, in particular for methane. With that, that's it for a brief introduction of gas detection using hyperspectral cameras. So I will now like to introduce, it's my pleasure to introduce our speaker for today, our guest speaker for today, Jesus Belmar. He's a predoctoral researcher currently pursuing his PhD at the Infrared Laboratory, Universidad Carlos de Madrid. His work focuses on the detection and quantification of gases emitted from leaks and flames, among other sources. He has several years of experience in gas sensing technologies and infrared spectroscopy, contributing to the development of advanced methodologies for environmental and industrial monitoring. We're very excited to hear about his research today, and I will allow him to kind of take over here.
Hello?
Hey, Jesus, let me change the screens here and give you some control.
Okay.
Let's go to change the presenter, Jesus. All right.
Okay. Let me a second. Okay. Okay, can you see good? All good? Yeah. Thank you, Chris. Thank you all for being here. For my name is Jesus Belmar. I am a PhD student at the University Carlos III of Madrid, working in the infrared laboratory within the physics department. Today, I'm going to talk about one of my last projects in the field of the industrial flames, filtered measurement of unburned methane emissions in laboratory flames using mid-infrared hyperspectral imaging. But before we dive into the main topic, let me give you a brief overview of our research group. We work on different lines of research and focus on infrared technologies. The first one is the thermography work. Here we work with different cameras in different bands of the spectra and get some image, infrared image like this. Let me here. And the second one is the gas detection and quantification. This work is a perfect example of that, so we will see. And the last one is aerosol detection and quantification when we measure the scattering of the particles. Among them, I like to highlight a couple of projects that marked our first steps combining hyperspectral imaging with the flame measurements, okay? Or hyperspectral measurements we did with the Telops Hypercam, all of these, okay? These projects are called Empress and Empress 2. In both, we studied a standard flame to create temperature and concentration of carbon dioxide maps across the entire flame. In the first project, Empress, we achieved very good results using only hyperspectral system. Okay, we can see here the maps that we obtained for the temperature and concentration. And then in the Empress 2, we focus on testing a much simpler and more portable device like a multispectral camera. This camera works with a filter wheel with different filters in different bands of the infrared spectra, and then use a hyperspectral systems like a validation tool. Okay, we can see here the results, that are very good results, as you can see in the figure. Then showing that the hyperspectral setup has a strong potential as a validation method. This is an important point that we will see in all this work. Okay, Empress and Empress 2 were past projects. Today, and as the foundation of the work I am presenting, we are focused on a new project called Memory. This is a public-private partnership where we work closely with Sensor Solutions, a company based in Madrid specialized in infrared technology. The motivation behind this project can be summarized in 3 key points. The first one is methane is a greenhouse gas that is about 80 times more powerful than carbon dioxide. The second one, methane emissions from industrial flares have often been underestimated, mainly because measurements were not taken directly in the field. And the last one, there is a clear need for reliable measurements of these emissions, but doing so in real-world conditions is very challenging due to technical limitations. With this in mind, our main goal at the MWIR project is to measure the flow of unburned methane released into the atmosphere by industrial flares. To do that, our approach as a research group has been to design a validation method that allows us to test and validate field instruments in a controlled laboratory environment, following a similar strategy though the one we use in Empress and Empress 2. Finally, the impact of the project is clear to help reduce the carbon footprint of the industrial sector. Okay. Now that we covered the background of the project, it's important to take a moment to review the current state of the art. This will help explain the motivation behind each of our innovation. Okay, we can divide the state of the art in two topics. One is for laboratory scale. In the laboratory scale, we can find two important methods. The first one is extractive methods in laboratory flames with assisting fluid. This fluid can be air or steam. And the burner here have a perfectly coaxial air assistance. Okay, here we can see in the image that the assisting fluid is in the center, and in the external ring is the fuel output. Okay. This type of method is a good method for measurements, but is a not realistic method for generate unburned emissions. Because if we see this plot, that in this plot we can find the combustion efficiency as a function of assisting fluid, we have a jump between the 100% to 0. This limited the analysis of unburned compound evolution. Okay, that is important because we have a jump to 0 rapidly. So the next study in the laboratory, more or less scales, we have extractive measurements in a wind tunnel. For these measurements is a more realistic condition because we have a crosswind effect for the flame, and the flare is more realistic because it's bigger than this one. But the problem is we cannot see the flame dynamics, and the measurements are samples because we extract the flux of the several gases in some points of the tunnel, but we can see around the flame. Okay. So now the second topic is more realistic scenarios. Okay. The first study are extractive method 2, but in industrial flares. If you see the image, we can see the problem because the dimension of the extractor is in comparative with the flare dimension. Okay, and this involves localization sampling, which may be not representative of overall flame behavior, and no certainty about what is truly being captured at the sampling point. This is an important problem because maybe here we can extract carbon dioxide and the methane is here that we will see. So the extractive methods have good results, but remote sensing is a very good way to get a measurement about the flare and about the dynamics of the flare, dynamics of the emissions, of the burned emissions. So we start to talk about the problems with the remote sensing measurements. The problems, like when we work in the mid-infrared wavelength, it's important that we will work in this window because it is a atmospheric window. We have very good signal for the methane, that is the interest of the project, but the problem is we will have carbon dioxide. Okay, the emission of the carbon dioxide is higher than the emission of the methane, and we will get more carbon dioxide in the combustion products. So if we set the integration time for our detector to measure the cold methane, the detector will be saturated by the carbon dioxide. We can understand better this with an example. Here we have a flare and a spectra of the flare. With the blue circle, we have the signal to hydrocarbons, and in the green circle, we have the signal of the carbon dioxide. So the problem is, if we have to set the integration time for measure that, this signal will saturate our detector. Okay. So how we will solve this problem, because there are interesting results in all of this work or in all these studies, but our proposal can divide in different points. The first ones, we will work with a remote sensing method. Okay, remote sensing method combining Telops Hypercan and optical filter. Later I will talk about the optical filter. The second point, we will work in laboratory scale. Why? Because we want to be a validation method. Remember that. So for validation method, for a good validation method, we need to be controlled, to repeat the measurements, and accurate to perfect results. Okay. So we work in laboratory scale. So we can do something like work in absorption mode. Absorption mode, for absorption mode, we will need a hot body in our scenario for get absorption spectra. And because the burned fuel is have a low temperature compared with this body, so we can work in absorption mode because we are on laboratory scale. Okay, then with remote sensing, we can measure the flying dynamics and the dynamics of the unburned fuel. Okay, and with this we can combine all of the results to measure the flow of the unburned emissions. Okay, so now I will explain all our innovations to the last studies to get this proposal. The first one, we will use a black body, like I said, but to understand this, I will talk about the different spectra. First, we have emission spectra. Emission spectra mean like hot methane. In this case, temperature of methane is higher than the temperature of the background. Okay, and we have the peaks or the lines of the spectra of the methane above for the baseline. Okay, this is an example. This is a spectra of methane. This is other gases, but here we have the methane. And then when we work in absorption mode, we will have cold methane because the temperature of background will be higher than the temperature of the methane. And then the peaks or the lines are below the baseline. Okay, the baseline are different in two spectra because here the temperature of the background is less compared with the temperature of the background in absorption, because here we have a hot body, the black body. Okay, with that we can talk about now to the black body. Our background, the black body, set to the temperature 500 degrees. This is because this temperature is near to the temperature of the ignition of the methane. Okay, this is important because it enables us to distinguish between cold methane, that is unburned methane, because it's lower than 500 degrees, the ignition temperature, and distinguish between this and hot methane, that is methane about to burn, is emission. For this methane, we will get a spectra like that, and for this methane, we will get a spectra like that. This is an example, a scheme of the setup. We have a black body, a flare, and the Telops Hypercan. Okay. The next innovation is the optical filter. We use this filter. If we see the image of the transmittant of the filter, we have the black line. The black line is the transmittant of the filter, and the orange line is for the is an example of the spectra of methane. Okay, we can see that the area of the filter fits perfectly with the methane, and with that we can avoid the signal of the other gases like carbon dioxide, water, and more gases. With this, we only see methane in all of the spectra and results. Only see methane, avoid these gases allow us increase integration time now, because the carbon dioxide won't saturate of the detector. And then if we increase the integration time, we will improve methane signal quality. Okay, this is important to get better results because we will improve our spectra. And the last step, or the last point on our setup, is the burner. The burner is very important because we design our burner thinking in the stripping mechanisms. For me, is the moralistic way to get unburned fuel. So the effect is like we have crosswind in the real scenario. The flare suffers this crosswind, and then the fluctuation generates a fuel pocket. This fuel pocket is the blue pocket, and this pocket gets other way different with the flame way. Okay, the flame path. And then this is a cold pocket. This is unburned fuel. So get out to the flame zone, to the combustion zone, and is emitted to the atmosphere. Okay, but for this effect, we need something like a crosswind effect, something like, because we work on unburned in the line of the air assistance, because we have a fuel output and then our external ring with air output. But the important point is that we tilted a little bit the external ring. With this tilted, we get something like that. In this image, we can see our flame without assistance, and then when we put the assistance, get this effect. It's a crosswind effect. We haven't something like a ventilator or something like that. We have crosswind effect only with the external ring and tilted. Okay, the combination of two things. With that, I talk about the all setup, but now how to obtain quantitative results, because the setup is good, okay, but we want results. So we have two ways. The first one is experimental way, and the second one is for the model. Okay, we start with experimental that we will measure, then pre-processing our spectra, and finish we get experimental spectra, a clean experimental spectra. And in the other way, we have to define our radiometric model, because it's important to get a simulate a scenario, or a scenario. We have to simulate this scenario to get a simulated spectra. Comparing both, we will retrieve concentration and temperature. That is our goal in this way of the work. Okay, so I will talk about these points. The first point, I will start with the model, is the radiometric model. We have the radiative transfer equation, a big equation that have two terms, one for the emission of the background, and the second one, the integral term, is for the emission of the gases. If we talk about term by term, the first is the incoming radiation to the detector, that now have a scheme. The second one is the background radiation. In our case, is the black body radiation, that is this arrow. Okay, and this radiation suffers a transmittance effect, because cross a medium, then flame, and then medium. Okay, this is the transmittance. And the next terms is for radiance emitted by the gas, and the purple term is the radiance absorbed by the own gas, because here starts the radiance and get absorbed by the own gas, and then gets absorbed by the medium and arrive the detector. Okay, with all of that, we can talk about now the approximation. We did a different approximation, but the point is we consider the medium homogeneous for the temperature and concentration. This is unrealistic, so we work with effective values for concentration and temperature. This is a summary of the approximation, but I don't talk about one by one. So we get finally this equation. This equation depends of the temperature and the concentration. That is our goal. Our goal is to retrieve these parameters. Okay, with the radiometric model, I can talk about the analysis that we did. The first, we did a ratio. Why we use a ratio? Using a ratio, we can eliminate different contribution. The first one is the transmittance of the instrument optics. The second one is the optical filter. The next one is the term for the atmosphere between the flame and the instrument. And the last one is the detector's spectral response, okay? And the ratio is by measurement of a scenario with flame and the scenario without flame, okay? This is important. And with this ratio, using the radiometric model, we get this formula, okay? This formula has two terms. The first term is the usually known light transmittance, and the second term is for the emission of the gases. Usually, when we work in absorption, we get the transmittance because we get only cold gases, okay? But in our case, we can neglect this term. We cannot neglect this term. Why? Because we have hot gases, methane of the flame, methane that get more temperature than, get higher temperature than 500 degrees. So we cannot neglect this term. With this formula, we can now talk about our experimental effective transmittance, okay? This is like a transmittance, but not, because when we have emission, the value of the transmittance will be higher than 1. And when we have only transmittance, the value of the transmittance will be lower than 1. So we will talk about effective transmittance, okay? This is the equation. S is the experimental spectra, and S0 is the offset. We will measure the offset with a cold body in front of the detector, and then eliminate the contribution to our measurements. Then we have our model, and then we have to clean the experimental spectra, okay? For this clean, we start with the median for each pixel of 25 measurements. For that, we have 25 measurements, 25 data cubes, and then we will do the median and get only 1, okay? The next step, we'll do a spatial convolution with a 5 by 5 pixel window. This is an example. In red, we select the window, is array 5 by 5, and then in each pixel, we have one spectra, one S2 spree, and then do the mean, here the mean, and get the same spectra for the window. And then it's a convolution, so the window will move around the image, okay? So now we have experimental function for effective transmittance. We'll have our model, so we can simulate a function for different values of concentration and temperature. For that, we will use the spectroscopy parameters of HITEM database. HITEM database is an extension of the HITRAN database. HITEM is better for hot gases, and we try with both, and we get better results with HITEM. Okay. And then we will minimize the sum of square errors, solving this equation to obtain the optimal parameters for the fit. This is the equation, but it's a software implemented in MATLAB, so I don't talk about that. But with the model, we can get the experimental transmittance, effective transmittance, and get values of concentration of temperature that fit with the experimental. Okay. Now I talk all about the model, about the measurements, but now we want to see the results of that. Okay. So the first point is like we have this hyperspectral image, but there are 4 images. Okay. Why? Because we have a limited area for the black body, for the background. So we have to move the area around the image to get one image of all flame. Okay. We can consider that it is simultaneously because like I say at the beginning, the flame with this condition is very controlled. Okay. Then this is the crosswind effect. We can see the shape of the flame. This image is in digital numbers, so we have a frame of the interferogram. We don't have information about nothing here, so only the shape. And now I will focus my work, my analysis in region 1. Why? Because for the dynamics of the flame that we will see in the shape and the crosswind effect direction, here we'll get better results. Later I will talk about the other regions. Okay. And then in this region, we select 4 pixels, pixel 1, 2, 3, and 4, and get a experimental measurement and a fit. The experimental is the black line, and the fit is the red line. Okay, the fit is very good, as we can see. And in the left pixel, in the 1 pixel, we have more concentration values, high concentration values, and in the right one, in the 4 pixel, we had lower concentration values. Okay, this is what I would expect, that we can see here the peak is higher than the peak in the last one. But the important point is here we haven't flame. It's background, and we can see perfectly the methane. We can see perfectly the methane. So it's unburned methane. We are generating this type of unburned fuel. So if we repeat these fits for all pixels, we can get this type of maps. The first one is column density map for each pixel. The second one is the temperature map, and the last one is the fit error map. Okay, is an error of temperature or column density is the fit error. Okay, it's important. So here we place the burner to note what we see, and then for the column density, the color bar is saturated in 50 because our interest zone is here, because the unburned fuel is here. Okay, this is flame. Now here we have fluctuation and we have an unburned fuel. Here there is the unburned fuel, so the interesting zone is this one. Okay, so we feed the color bar to this zone. Then for the temperature map, we have good result because here we have low temperatures because it's near to the nozzle of the burner, and get more low temperatures here. Okay, and the last one, the fit error map, is very important because okay, we can see high errors here, but it's not a problem because our region of interest is this one, and in this zone we get very good errors. Okay, with the errors and concentrations, we will define our control line. Why? Okay, we need a control line because if we go to the flow equation, because our goal is get a flow, now we have to define a flow model. So we start with the flow equation that we have the mass per time that cross a surface. Okay, this depends of the density of methane and the velocity of the gas. So we have to we need to define a control surface. The next point, okay, we have density, but we need the velocity. So we have to measure the velocity at each point of the surface. Finally, using the velocity and the concentration maps, we can get a methane flow with this equation. Okay, now I will define our system in the coordinates. Okay, here we have in blue the control surface, but in the maps I talk about a control line. Why? If we view in the point of view of the instrument, we get the surface is aligned. Okay, we will use 2 lines for get better result of the dynamics pockets, but we will see later. And with this and with this equation, we get this formula for the flow. Okay, here we have the concentration and the velocity, all depends on y, because we have to do the math with the points of the control surface that only depend on y coordinate in this scheme. Okay, so how we obtain the velocity? To obtain the velocity, we'll use 2 operation modes of the Telops hypercam. Where when we do a measurement, we get an interferogram. Okay, we can work in the interferometer mode to get the concentration, because we get a spectra. With the spectra we can fit and then obtain concentration that we see before. But there are other modes. The next mode is high-speed camera mode. Each position of the mirror in the interferometer is at each point of the interferogram. Okay, and each point of the interferogram is a frame of an image. If we see all interferogram, we'll finally get a video. Okay, Of course, we have one interferogram for each pixel. So if we combine all pixels, then we get the frame of the image and then the video. Okay. With this mode, we can see here we haven't the interferogram. We have the effective transmittance because it's better to understand what is here. Okay. I play the video. Here we have 3 colors. The orange color is for the background. Okay. And the important colors is red because it's hot methane. Like I said, is effective transmittance higher than 1. And the green color is for cold methane, that is lower values of 1. Okay. Here we can the dynamics. Now we are seeing the pockets. Okay. This is the dynamics of the pocket generation in the setup in our setup. Okay. With that, now we can work in a software of tracking. There is a software implemented on MATLAB that can select a pocket and then track the pocket. If we know the interval between the time interval between consecutive frames, and we know the position of the pocket in between frames, we can get a velocity for each pocket. Okay. This is a software implemented on MATLAB. We only applies on our videos. And then if we combine, if we do for all pockets, we will get a field velocity map, and combined with our map for the concentration, we can get the flow. Okay, we define this control line. We now have a velocity for each point of the control line, and here we have the concentration for each point of the control line, and we get the flow. We use this equation where we apply several changes using the ideal gases equation to get our units. Okay, and we get these values. Okay, now we have a flow for the methane, for the emission of methane. And now I have to talk about the destruction removal efficiency. It's important, very important value in the industrial sector. This value only depends of the unburned fuel emitted to the atmosphere and the initial or injected fuel to the flare. Okay. Combined, both here we measure our initial fuel with a mass flow method, and with the mass with this flow that we obtain, we can get their destruction removal efficiency value of 94%. This is an upper limit because we only analyze the region 1 for these values. Okay, we only obtain results on this zone for this number, so it's an upper limit. Okay, that's it, and this is an important point because the value of the rate of destruction removal efficiency 1994, we can see that is a very good because as it is quite realistic when compared with other studies on the industrial flares. Science or method aims to be a validation approach. Obtaining a realistic results for our burned is very positive for the future validations. Okay, so now why I neglect the other zones in the process to obtain the flow? Because when we analyze the region 2 and 4, we get a concentration below detection limit in the spectra. Okay, and by the dynamics of the flare with our crosswind setup, we get not trackable pockets in the image. Okay, so we can ignore these both regions. And for the region 3, we get some interesting results because if we see these frames of the one video, we get here in frame 1 pocket, and in the frame 11 we get flame. We don't know if the pocket is emitted to the atmosphere or the flame or is born getting flame here. Okay, maybe all of this pocket is born for this pocket are in the combustion zone, but we can talk about that because we need to black body with larger area or extend the analysis or the measurements of the region to more regions of the flame. Okay. And then, summarizing and concluding, we will talk about the problem. The problem is to quantify unburned methane, and to visualize its dynamic is very difficult, even for the most advanced remote sensing instruments. Our proposal to solve the problem is, like I explained, we combine Telops Hypercam mass plus filter, and then we work in two modes: interferometer mode to get an absorption mode. Combine both, we get concentration and temperatures. And then in high-speed camera mode, we get the velocity. Combined the three values, we will get methane and then destruction removal efficiency. Okay. With that, our method allows us to determine the methane flux emitted into the atmosphere in the form of the pockets. Important result. It allows the study of pocket dynamics under controlled conditions, a fundamental step toward understanding the mission and behavior of pocket in industrial flares. The next one, we have obtained an upper bound of the destruction removal efficiency value, a variable of great importance in the industrial sector. This method can be used to validate other field techniques. That is the principal proposal of our method. And then finally, Telops Hypercam is not only a powerful field instrument, but also a highly valuable research tool. And I conclude with that. Thank you for your attention, and I open to your questions.
Right. Thank you very much, Jesus. That was very informative. I know I learned a lot. Okay, yeah. So if anybody has any questions or comments they would like to make, please use the questions box in the GoToWebinar. We'll try and answer a few of them live here. Yes, I can. I actually have a few questions. When using when going for high speed, do you remember what kind of frame rates you were using for this?
Frame rate.
Yeah. Do you remember what I'm just kind of curious on the frame rates you guys might have been using.
Oh, I have to remember. I think it's 200 frame rate for our instrument.
200. Okay.
Hertz. It's Hertz. I will talk in Hertz. Okay. No, it's
yeah.
Okay.
Yeah. Let's see. We'll also remind everybody that any questions we're unable to get to, we will be able to answer in written form and send later. Okay, let's see. I have a question here, and I'll try and shoot that over to you real quick. The question is, thanks for your nice presentation. If you have any practical measurements for the methane.
Practical measurement for the methane?
Yeah, I think they're asking if you have any practical measurements for the methane.
But what is practical? What mean practical measurements? What exactly is the practical? I think maybe he refers to a realistic or scenarios or something like that.
Yeah, we can maybe try and expand on that side of it. How you see this kind of playing into realistic scenarios.
Well, we not try to realistic scenario because we focus our work in, like I said, in validation method to validate other instruments like cameras. we try with other things, but we can measure on absorption mode because our method is based in absorption mode, so we need a black body in our measurements. So we can do in an industrial flare, for example, because we have to elevate the black body.
Yeah, so kind of on that, you know, so you're doing these laboratory measurements, and this kind of really allows you to dive in and look at very specific dynamics of what's going on in measuring unburned methane. And that's is there kind of a next step after that? So once these laboratory measurements, and I know it takes a while, but once you feel like these laboratory measurements have worked well enough, and you kind of see another step forward other than just going out and trying to measure the flares again, is there an in-between step there, or is it strictly, do you think it's strictly laboratory driven, trying to continue to work with laboratory flames?
Yeah, we continue in both ways, because we try with more bigger flares, okay, and we try to do with different condition of air condition, and one of our goals is validate something like Empress and Empress 2. We can validate some maybe cameras and try to measure in real scenario with cameras, with spectral cameras, and we work in other type of method, but all in laboratory scale, because always we try to be a validation method, because the hyperspectral instrument is our treasure, okay? So we try laboratory measurements for validation of other field instruments.
Okay. Thank you for that. Let's see. We'll do one more here. Do one more question here. I will send it over to you. And the question is, great talk. I have seen studies hypothesize that cold methane sinks down the flare that cold methane sinks down the flare stack. Thus, if you're trying to measure methane using extractive methods, you could miss the methane. Did you investigate the specific paths of the methane pockets?
Okay. Yeah, we try extractive methods too, and we can, with our remote sensing method, we view that the mechanism of the generate environments is that we say in the video, in the presentation. So we can see the path of the pockets is, like he said, is we define the control lines in this way to get this path that cross the surface that we define. So we can see with the videos, we do several experiments, trying several conditions and see several things, but the perfect generate unburned is with this method, because we can track this type of pockets, and we can track the path of the pockets, like he said, in this direction. But with extractive, we will work with different setup for extractive methods, but it's more or less complex, because with the pockets we have to imagine a extractive method to this pocket, but we are working on that.
Okay, cool. Great. Thank you, guys. Thank you, Jesus. I think that'll be the last question we have for today. I would like to thank all of you for coming, and I'd like to thank all of you for attending this webinar. I would especially like to thank Jesus for being a guest speaker today with us. The insights that you've given us they were really great. I know I definitely learned a lot. It's very informative, and I hope everybody else found it informative and valuable.